Hello, calculus students. In this section, we're going to learn how to alter a series. We're going to start with a known series and alter it. We're going to go over 5 different ways to do it. These strategies are very useful for making new series, so you don't always have to create them from scratch. One will be compositions, which just means replacing the x in the statement with something else, like changing all the x's to 2x, for example. We're going to be able to differentiate a series to create a new series. We're going to be able to integrate series to create a new series. We're going to be able to multiply a series by constants or powers of x or some combination of that. And we're going to be able to add terms to series. We'll illustrate these one at a time, what it means and what the effects are on, say, the interval of convergence. Let's do a composition first. Find a Maclaurin series expansion for the given function. Write the first 4 non-zero terms and give the interval of convergence. We're going to be able to find a series for this new function by simply altering the series that I've already created for the natural log of 1 plus x. And we're going to do it by using a composition. Here are the 4 parts of our statement. We have the function that we use to create the series. We have the resulting creation using summation notation. And we have what it looks like in expanded form. And we have the interval of convergence. If you make a change here, then make the corresponding change here, make the corresponding change here, make the corresponding change there. In this case, all we're going to do is replace x, and this x right here, we want it to look like that instead. So we're going to replace x with negative 5x. This is a composition. So the function will now become natural log of 1 minus 5x. Now I'll change all the x's in this statement to negative 5x in all pieces of it. So we have our series starting at k is equal to 0 and going to infinity. Negative 1 is still being raised to the k, but the x changed to negative 5x. And make sure you use parentheses around that negative 5x. That's being raised to the k plus 1 over a k plus 1. And it's really that simple. There's the series. Now what does the series look like if you start putting some terms out? We could do this 2 ways. You could just copy this one here, but by changing all the x's to negative 5x, or you can actually change all the k's to 0, then to 1, then to 2, and see what you get. Let's do that way. Let's make all the k's be 0. So in the end, we just get negative 5x plus. Now let's change k to 1. Negative 1 to the k, when k is 1, will be negative. So I'm just going to make this subtraction here. This k goes to a 1, so we have negative 5x squared. And then over, and we change that k there to a 1 as well, we get over a 2. Notice we're going to get this again, but all the x's will be replaced with negative 5x in parentheses. So now I'm going to just shift gears and look to this to get my next term. It's going to be plus negative 5x cubed over 3. And then I'm not going to bother with the next one. Let's say dot, dot, dot. Now, our interval of convergence has to be tweaked as well. This function will be equal to this series for the following choices of x. Write this again, but do the composition. Change the x to negative 5x. Make one more line to simplify some of these things. We'll call this done. I don't recommend tweaking this. Really, you don't have to. It would be nice to simplify some of these terms here. These parentheses aren't needed. When I square negative 5x, square the negative 5, you get 25, and square the x, you get x squared. And so the negative in the front will remain, and this will be 25x squared. When I cube negative 5, it goes to negative 125. I can just make this subtraction. And then the last thing I want to do is actually solve this inequality for x again to find my new interval. Divide everything by negative 5. And because you're multiplying or dividing by a negative number, you need to switch the direction of the inequalities. So we're going to get a positive 1/5 over on this side. The directions of these inequalities will switch, and we'll get a negative 1/5 on the other side. And we get a new interval of convergence. The simple composition took us from a familiar series, we'll call it a parent series, and we were able to tweak it and create a similar but different series. The next way was to differentiate. We're trying to find a series for this function. Turns out that that is the result of differentiating the geometric function for the geometric series. So we're going to differentiate. Okay, when I do the derivative of the function, I do get 1 over 1 minus x squared. But now I have to differentiate everything. Let's focus on how to differentiate this part here first. When you differentiate a sum or a series, you can just differentiate it term by term. Differentiate 1, I get 0. Differentiate the x, you get 1. Differentiate the x squared, you get 2x. Differentiate the x cubed, you get 3x squared, etc. You can also differentiate the summand. You could really just focus on differentiating this, treating x as the variable and k as a constant. When we do that, the k drops down, x, and the new power is k minus 1. Right, and there we go. It turns out that a differentiation and integration do not change the radius, but they may affect the endpoints. You have to do a separate analysis to see if the endpoints are no longer included or are now included. Now, since the first term of this is 0, sometimes you see a shift in the summation happening. Instead of this being the k equals 0 term, and this being the k equals 1 term, and this being the k equals 2 term, they effectively do a switch because we don't care about having the 0 term, so they shift these over and they rewrite the series so that the k equals 0 term corresponds to 1, the k equals 1 term gives you the 2x, etc. If you do that, then the way you would write this series is start it at 0 still and go to infinity, but put a k plus 1 here and just an x to the k. Right, so you plug in 0, you're going to get this term now, not this one. When you plug in the next k equals 1, you're going to wind up getting this term. When you plug in k equals 2, you get this term. So don't be confused. This series right here and this series right here produce the exact same 1 and on. You can alter a series by integration. So we're going to want to find a series for cosine. Now one thing I could do to go from sine to cosine is I could differentiate it. Differentiate this, differentiate this, differentiate that, and then we have no change in radius. So it'll be the same interval. That's actually the preferred way. But I'm going to do this using integration just to show you how integration is done. The antiderivative of sine is negative cosine. Here we're going to integrate all of these one at a time. So integrate the x. That gives you x squared over 2. And then minus. Integrate x cubed over 3 factorial. That gives us x to the 4 over 4, and there's already a 3 factorial there, but 4 times 3 factorial just becomes 4 factorial. Plus, the next one would be x to the 6th over 6, 5 factorial there, but the 6 times 5 factorial is really the same thing as just 6 factorial. The next one would be minus x to the 8th over 8 factorial, etc. Also, when you integrate, you have to remember that a plus c gets generated that we cannot ignore. Put the plus c at the start. And let's just pause at this moment right here and see if we can figure out what that c would have to be so that this statement is true. We want to pick a value of x that's going to cancel the series out. And the obvious choice to pick here is 0. Right? If you plug in 0 for all the x's, then all the terms of this series will 0 out, leaving just the c. Our goal is to find c, and we're going to do that by letting x equal 0 on both sides. So plug in 0 into the function as well, so we get cosine of 0 is 1, so we get negative 1 over there, and then we get c plus, and then we get a series of zeros essentially, which is just 0. So in other words, c has to be negative 1. Okay, so we found that c has to be negative 1, so we can change this c here to negative 1. Here's the series for negative cosine of x. Oh, and that doesn't change our radius, by the way. So if the radius here is infinity, which it is, then the radius of our new series will also be infinity. So it's going to converge for all choices of x. Now, I wanted cosine of x, not negative cosine of x. So I could just multiply both sides by negative, change all the signs here. And let's figure out how to write this as summation notation. You could also just, integrate this, treating the k's as constants and the x as the variable, and get a series that way too. But let's just try to reconstruct it from these terms. K equals 0 to infinity, and we have even powers of x. So I see x and to make an even number, it would be 2k. Let's just test it. If you plug in 0 first, you'll get x to the 0, which is 1. So that does give us this. That's good. When you plug in k equals 1 next, you get this one. Then k equals 2, then k equals 3, etc. So our powers of x look good. Now we want to get these factorials in the bottom. Well, it looks like the exponent and the factorial always match. 4 factorial, 6 factorial. So we should have a 2k factorial. And then we also have alternating signs. Negative 1 to the k, let's see if that does the job. If not, we'll do k plus 1. Plug in 0 for k, and you get positive 1. So yeah, we get a positive to start like we want. So there we go. There's our series, and the radius will be the same. So this will converge also for x between negative infinity and positive infinity. Now notice, we could have done this pretty easily by differentiating. And let's look at this. Derivative of sine, cosine. Derivative of x, 1. Derivative of x cubed over 3 factorial. Let's test that. The 3 would come down, the power would go to 2, and there's over a 3 factorial, but 3 will cancel with 3 factorial, leaving a 2 factorial. So it does produce this term. If I were to differentiate this positive x to the 5th over 5 factorial, would I get that? The answer is yes, right? Because the 5 would drop down, the power would drop to 4, and it's over a 5 factorial, but that would cancel, leaving a 4 factorial. So differentiation actually works very well. It's a little bit easier to do than integration, because integration introduces the complicated element of the c that you have to worry about finding. Also, this expression here is very easy to differentiate, right? The 2 plus 1 would drop down. The negative 1 of the k would still be there. That's a constant. 2k plus 1 would drop down, and the new power would just be 2k. And this is all over a 2k plus 1 factorial. But this 2k plus 1 will cancel this 2k plus 1 factorial, leaving it just a 2k factorial. So it does produce this pretty easily. Well, anyway, this makes a cosine series. We're going to use this cosine series as another parent. You can alter a series by multiplication. So if I want to create a series for 3x squared times e to the x, this would not be a good one to do from scratch, because the derivatives, right away, you have to use product rule, and then it just worse and worse and worse. So making a table would not be ideal. Instead, just start with a series for e to the x and then multiply it by 3x squared. Okay, so here's the one we're starting with and all of its details. And let's multiply everything by 3x squared. which means you can distribute the 3x squared with the summand. So we have 3x squared times that. Sometimes you'll see people combine these and say x squared times x to the k can be written as x to the k plus 2. The next line of our work is to multiply the series by 3x squared. When you do this kind of alteration on a series by multiplying it by a constant by a power of x, this has no change on the interval of convergence at all. And really the only thing I'm going to do now is I'm going to actually do this distribution here. We get 3x squared as the first term now, plus 3x cubed, plus 3x to the 4th over 2 factorial, 3x to the 5th over 3 factorial, plus dot dot dot. And we have this same interval of convergence. So that's a pretty easy way to alter a series. And the last one is by adding stuff to a series. If you have a function and then you have a few terms added to it, let's write it this way. We're going to add 2 plus 3x squared to all three components of this. You're going to add it to the summation notation form and an expanded form. And doing this also has no effect on the convergence. So we have 3x squared plus 2 plus natural log of 1 plus x. Do some zooming in here. Don't bother with pushing these terms in there. Just leave the series and the other two terms separate. Okay. But over here, we might as well actually combine similar terms. The 2 here doesn't combine with anything here, so we just get a 2. Right, the x was not affected by this, right? There's no x term here, so that one stays the same. But this 3x squared and the negative x squared over 2 are similar, so we get to combine their coefficients. That's essentially 3 minus a half, or 6 halves minus a half, that's 5 halves. These are the only two terms, the constant and the x squared term, that are going to be affected by this. All the other terms of the series will be the same. And this would still be true for this interval. All right, let's get some practice doing combinations of these things. Let's begin with this arctangent. I'm going to, of course, guide you on how to start with this geometric series. And through these 5 ways to tweak, I'm going to turn this geometric series into the arctangent. And the goal is to figure out what those steps are and in what order to go from the geometric to the arctangent. Sometimes it's easier to do this backwards. Try to figure out how to go from arctangent to that, and then just go the other direction, reversing all those steps. All right, so we have the arctangent. I know that if I differentiate it, it turns into this. Well, this looks pretty similar to this one. There's a derivative connection here, and then some sort of composition happens here, but I'm really interested in the reverse process here. I want to start with this one and go to that step and then to that step. So from here to here, I'm going to do a composition. I'm going to change all the x's to negative x squares. And then to go from here to here, we would integrate. So this provides my 2-step schematic for how to start with a known series. We'll do this composition to make a series for this intermediate step, and then we'll do this change to get to a series for what we want. That is our ordering. So let's do a composition. So we're going to replace x with negative x squared. And we're going to do that everywhere here. So that gives us 1 over 1 plus x squared equals, change this x to also negative x squared, and that's being raised to the k. And then change every x in this statement to negative x squares. And when we do a composition, make sure that you also do the change for the interval as well. So we get negative x squared is between negative 1 and 1. Before I do the next step, I'm going to simplify this, and then we'll worry about doing that last step to get to the arctangent. This would actually be a lot easier to integrate if I simplify this. This k affects the minus 1 and the x squared separately. So we have a negative 1 raised to its own k, and then we have an x squared raised to the k, which will just become x to the 2k. Let's get rid of some parentheses here. This will become subtraction minus x squared. This square is going to kill that negative, so this will be positive, and then x squared squared is x to the 4th. The next one will go negative again. Cube the negative, it stays negative, and cube x squared to get x to the 6th. So the next one will be plus x to the 8th. Now this part here, I'm going to get rid of that negative sign first. I'm going to multiply both sides by negative 1, and that's going to change the direction of inequalities. 1 is greater than x squared, which is greater than negative 1, which you could flip this around and put the negative on the left again and right. And then if you actually look at a graph of this, x squared looks like this, and we want the output of x squared to be somewhere between 1 and negative 1. Really just means that we have to figure out which x coordinates where it intersects that upper line, and that means that if x is between negative 1 and 1, so if you stay within these vertical lines, then that will guarantee that x squared, which is the output, stays within these horizontal lines. X itself has to be between negative 1 and 1 still. All numbers between negative 1 and 1, when you square them, will stay between negative 1 and 1. In other words, it looks exactly like the original integral we started with, this one. Now we're going to do the integral. Okay, anti-differentiate 1 over 1 plus x squared takes us to arctangent. We're going to anti-differentiate this with respect to x. K is a constant as far as x is concerned. So the negative 1 to the k will still be there. But the antiderivative, use the reverse power rule, we're going to get a power that's 2k plus 1, and then you divide by that new power. The other side, we do have to get this c of integration. Then we integrate 1, that's just x. Then integrate negative x squared, that's negative x cubed over 3. Then integrate positive x to the 4, positive x to the 5 over 5, etc. And when you integrate, we do not change radius. So if this radius of convergence is 1, then this is going to be guaranteed that if I keep the open interval, we're going to get convergence. It might turn out that we get to keep the endpoints. Only the radius is not affected by integration. Okay, we want to figure out what c is, so just pick a choice of x. 0 is always the easy choice. Let's just worry about the function and the expanded series to find c. Let's not worry about plugging 0 into here. Arctangent of 0 is 0, because 0 is the angle at which tangent is 0. So we're going to get a c and then plus a bunch of zeros. In other words, c has to be 0. So I can rewrite this now, and without the c. And furthermore, if you plug in +1 or -1 for x, if we test this, plug in a 1 for that x, this will just become a 1. And so you're looking at a series of -1 to the k over 2k plus 1. That converges by the alternating series test. If you plug in -1, then -1 to the 2k plus 1. Since 2k plus 1 is always odd, it means that -1 to an odd power, this will always be -1. So this will still be an alternating series that converges by the alternating series test. So we actually get to wind up keeping both endpoints in this case. The radius doesn't change when you do integration, but sometimes the endpoints, whether they're included or excluded, do. And that's our arctangent. All right, one that we need to practice is the binomial. In this case here, it's good to express this in different ways. In order to use the binomial series, we want a 1 plus x. I have an 8 plus x. So I'm actually going to factor out an 8. So we have 3 over, I'm going to factor out an 8. That leaves a 1 plus x over 8. And all of this is in a cube root. Now I can cube root that 8 that's in the front separately. So it really winds up looking like this. Now I can write this as just simply 3/2 times, and then parentheses, 1 plus x over 8. This would have a -1/3 power on it. All right, so all of this manipulation was extremely helpful because it helps me recognize how this structure can be obtained from this starting point. I'm going to let r be -1/3. Then I'm going to do a composition and change the x to x over 8. And then I'm going to multiply everything by 3/2. Let's write this out specifically when r is -1/3. Okay, the next step, composition. Change all the x's to x over 8s. This new interval, multiply everything by 8, just turns into this interval. If x is anywhere between -8 and 8. And now we're going to finish by multiplying by 3/2. Just put a 3/2 in there. And then all of these terms will be multiplied by 3/2. Okay, and there it is. There's a series expansion for 3 over cube root of 8 plus x. Final thing I'm going to do actually is simplify these combinations. -1/3, choose 1. Pretty much r choose 1 is always just going to be r. So in other words, we just get a -1/3 here. Okay, now let's change the next combination. So -1/3, choose 2. In the numerator, start with -1/3. Then multiply it with a number that's one number less. So subtract 1 from -1/3. That should take you to -4/3. Do it until there's only 2 numbers, because that's what our combination is. And then divide that by 2 factorial. All right, so there's our expression that is -1/3, choose 2. Plus 3/2. Now we got to do this -1/3, choose 3. Start with -1/3 in the top. Go one number less. That takes us to -4/3. Go one number less. Takes us to -7/3. And we do that until there's 3 numbers, because that matches this 3. And then we divide that by a 3 factorial. And then the final step would be just simplifying this mess. And then we'll consider this one done. Looking here, we get cancellation of those 3's. Looks like we're getting a -1/16. The next one, we've got fractions within fractions. It would be a good idea to think of this as, instead of dividing by 2 factorial, we're multiplying by a reciprocal of that. Now we'll see what happens here. 3 cancels, this 2, and that 4 cancel. Don't forget you have to square that 8 as well. The square has to affect the x and the 8. And there's just an extra 3 down here. So we got to do 8 squared times 3. That's 192. We have a negative times a negative, so it's going to be positive. We have a positive 1 over 192, and that was times an x squared. Okay, for time's sake, I'm going to let you mess with this next one. So I'm just going to delete that and let you worry about doing that on your own. Let's put our just ... here. All right, we would just keep this up, and if we had to generate 5 terms, we would do what it took to make 5 terms. And our interval of convergence is -8 to 8. So that's all the examples for how to tweak series and to get a new series. Now I just want to show you just a few examples of why series are useful. And the uses of series extend well beyond the scope of this course. They are very helpful in approximating things and analyzing situations for which we have no analytical solution. Anyway, I'm going to use a series to approximate the value of e. The function I'm going to begin with is the obvious choice of e to the x. This is a function of x. The function and the series will converge to each other, will be equal, as long as you pick an x that's in the interval of convergence. The only thing you have to figure out here is, hey, what x would you choose so that this function becomes this? So let's choose x to be 1 and just rewrite the series. This is going to become now a series of numbers and not a series that involves x any longer. So we just get e to the 1, that's just e, is equal to the series, and then change this x to a 1, and 1 to the k is just always 1, so that's just 1 over k factorial, from k equals 0 to infinity. Change all these x's to 1s, and we just found a series that will converge to e. Now, choosing x equals 1 was allowed because, remember, we're allowed to choose any x for this particular case. Now, I do want to show you that this works. Now, let's just type in e in the first place so we know how big e is in decimal form. Now we're going to create e by doing a series, 1 plus the next one was 1 over 2 factorial, and 2 factorial was just 2. So that gets us even closer to e. Add the next term, 1 over 3 factorial. 3 factorial is 6. Notice it's getting us closer to e, plus. The next term was 1 over 4 factorial. That's 1 over 24. The next term was 1 over 5 factorial. 5 factorial is 120. Notice how my answer is getting closer and closer to e every time I add another term. The next one is 1 over 6 factorial, which is 720. Look how close we are to e already. And let's just do one more. The next one is 1 over 7 factorial. And 7 factorial is 5040. So notice we're already very close to e, and we've only done 8 terms of this series. This suggests that the series is converging quickly to e. Now the series goes forever, so there's still infinitely many more fractions. When you add them together, that's only going to make up the very slight discrepancy between where we're currently at and the true value of e. So the size of the tail is extremely small at this point. The bulk of the work was done by the first 8 terms of this series. Now let's find an approximation that helps us figure out what pi is. I'm going to use the arctangent series for this because I know that if I start with the arctangent and I want to make a choice of x that gives me something that relates to pi, and I have to choose an x in this interval, the tangent of pi fourths is 1. So therefore the arctangent of 1 is pi fourths, and 1 is a choice in this interval. So I'm going to let x be equal to 1. Arctangent of 1, plug in 1s for all these x's. The next one, using the pattern I see already, will be plus 1/9 and then minus 1/11. Right, we just have odd denominators and we have alternating signs forever. Now, the arctangent of 1 is pi fourths. To get a series for pi, I would multiply by 4. This is a series that will converge to pi. Let's test it. And the best way to test is actually, because it's going to turn out we need lots of terms to do this. And so I'm going to write this in summation notation as well. And that's simply done by rewriting this part here, but change the x to 1. This will go away. We don't need to write that. And then also multiply by a 4. Let's type in what pi actually is. Let's create this series. If you're doing it term by term, 4 minus 4 divided by 3 plus 4 divided by 5, you're going to see it actually converges very slowly. It's going to take many, many terms to get to the point where we're actually close to pi. As I add more and more terms, it keeps dancing around pi, but honing in on pi. It's going to take too many to see this happen. So let's do a sum notation. Type in sum from k is equal to 0 is where we start. And then let's go to a capital N up here. Let's type in the correct summand. Now we had to actually do a 4 times negative 1 raised to the k, and then all of this was over 2k plus 1. So now I can just use this slider. So there's the first term only, is 4. When n is 1, we have 2 terms. There's the first 2 terms, the first 3 terms. Now I'm just going to let n play. Notice that we keep dancing around the true value of pi, but getting closer and closer and closer to pi. Let's control n. There's 101 terms here, and we're at 3.15. 1,001 terms, we're at 3.14259. 10,000 terms required, we're yet even closer to true value of pi. 100,000 terms, even closer, etc. So it does take quite a few terms for this particular series to converge to pi, but in the end, when you add them all up, you will have pi. All right, use an appropriate series to approximate the given value. I'm starting with a 4 plus x in a square root, which is a binomial series, and I'm going to want to change the x to a 0.1. If I had done a binomial series for 1 plus x, in order to make this look like that, x would have to be turned into a 3.1. But the binomial series only converges if you choose x's in this window. So this is outside that window. This would not be a good approach. Here's the series I want to do this for. Let's factor the 4 out. That gives me a 2 times the radical of 1 plus x over 4. This is a 1 plus x over 4 raised to the 1/2. So here we see what our binomial series is going to be. I'm going to start with just the basic 1 plus x to the 1/2. And let's leave the series part out and just do the other part. Go back up here to the binomial series, right here. Or we can even do this one. Here's the binomial series one we've already created. What I was saying was I'm going to go straight to this. I'm not going to bother with the summation notation. Just to save time, I'm going to use the result that we've already done, the square root of x plus 1, and it's equal to this series. This was done from earlier, so we are borrowing some previous work. This interval of convergence, by the way, was -1 to 1. Let's change the x's to x over 4 and double. Let's do both steps at once. So let's do the doubling part first. We're going to double the coefficients. Going to double that coefficient. It goes to 1. And change the x to x over 4. Minus. We're going to double the 1/8. That makes 1/4. And change the x to x over 4. And that one's going to be squared. Plus, we're going to double the 1/16. That makes 1/8. And change the x to x over 4. And that's going to be cubed. Okay, so in other words, if I follow these steps backwards, we really just found a series for the square root of 4 plus x. So square root of 4 plus x is equal to, and let's simplify this a little bit, 2 plus x fourths minus square the x, square the 4, and then multiply by another 4. That's going to be a x squared over 64, plus cube the 4, that's 64, times 8, so 512. So we have an x cubed over 512. And then there's more terms. We're just going to use the first 4 terms because that's all the terms we found. Now, of course, this has a new interval of convergence. The multiplication by 2 does nothing, but the composition certainly does. And we need to change this to x over 4 has to be between -1 and 1. So multiply everything by 4, and we get x itself has to be somewhere between 4 and -4. I want to plug in a 0.1. Is 0.1 in this interval? The answer is yes. In fact, it's very close to the center of the interval, which suggests that this series should converge pretty quickly. If you remember visually, when you were close to where you were matching the Taylor polynomials to the function, they behaved most alike each other close to where they were centered. Let's plug in the x equals 0.1, and that yields to a square root of 4.1 is equal to 2. Plug in a 0.1 here, that's 1/10. That's going to be a 1/40th, minus 0.1 squared, that's 1/100th. And 1/100th divided by 64 is 1/6400th. Plug in a 0.1 and cube it, that's 1/1000. So this would be 1 over 512,000. This is a series that will converge to the square root of 4.1. Let's verify that. Square root of 4.1 is 2.02 blah blah blah. 2 plus 1/40th. Look how close we are already just by doing 2 fractions. Minus 1/6400. Look how close the two numbers are already. Plus 1 over 512,000. And we've only done the first 4 terms of it here. But as we do more and more terms of that series, if you do all of them, all infinitely many of them, you will equal the square root of 4.1. We can use series to approximate integrals that I couldn't do by hand. This integral, I cannot integrate that. I don't know an antiderivative of e to the x squared. It's one of the classic examples of a function that has no known explicit function that is its antiderivative. So what we're going to do instead is we're going to integrate a series for e to the x squared. So we're going to start with e to the x, and we're going to change this into a series for e to the x squared. And let's just worry again about this piece and this piece. The series and the function converge for all x's. You want to make sure that you're working with an interval that lies within your interval of convergence. Otherwise, you're going to have a problem. Let's first figure out what a series for e to the x squared is. To go from this line to this line, I change all x's to x squareds. E to the x squared is equal to, and I'm just going to write this down, but change all x's to x squareds. So you have 1 plus x squared plus x squared squared. That's going to be x to the 4th, and that's over 2. Plus x squared to the cube. That's going to be x to the 6th, and that's over 3 factorial, which is 6. Plus x squared, and then to the 4th. That's going to be x to the 8th, and that's over 4 factorial, which is 24. All right, I could do more. You can see an obvious pattern here. X to the 10 will be the next one, and this will be over a 5 factorial, which is 120, etc. All right, what I'm going to do is I'm going to integrate this by integrating the series instead, and you can integrate term by term. The integral from 0 to 1 of e to the x squared dx is equal to, you're going to integrate all of these one at a time. Okay, and we can do more as needed if we want to get more accuracy. Now let's actually do these integrations. The antiderivative of 1 is x. So we're going to evaluate x from 0 to 1. The next antiderivative is x cubed over 3. Evaluate 0 to 1. Next one is x to the 5 over 10. Evaluate 0 to 1. Next one is x to the 7 over 42. Evaluate 0 to 1. And right, we could do more. Now actually evaluate. Plug in a 1, then plug in 0. So we just get 1 for the first evaluation. The next time we're going to get 1/3. Then we're going to get 1/10. Then we're going to get 1/42. Let's anticipate what the next one would have been. It would have been the antiderivative of that, which is x to the 9 over 9 times 24. 9 times 24 is 216. And then we would evaluate that. We just get a 1 over 216. Hopefully I did that right in my head. Or we could leave it off. I'm just going to remember it. All right, let's check this out. An integral from 0 to 1, and our integrand is going to be e raised to the x squared dx. 1 plus a third plus a 10th plus 1 over 42. The next one, if I remember right, was 1 over 216. And notice that as I do more of these fractions, we just have to integrate as many of them as I need to get within to a certain tolerance of acceptable error. But notice we are getting closer and closer to the actual integral. Pretty cool, right? And lastly, find the sum of the series. This one, we actually have to do a little bit of detective work and figure out which series we're going to use to figure this out. And recognizing these things as powers of a fixed base, recognizing these things as factorial numbers, but not all of them. If I start expressing these things in other ways, it's going to reveal which function we're working with. So this is really the same series as just doing 5 plus, that 4 is 2 squared, and that 2 I could say is 2 factorial. And then minus 2 to the 4th is 16, and 24 is 4 factorial, plus 64 is 2 to the 6th, and 720 is a recognized factorial, that's 6 factorial. Ooh, this looks very familiar, right? I'm guessing the next one's going to be minus 2 to the 8th over 8 factorial. The only thing that doesn't follow all the pattern is this part right here. And I wonder which series involves doing even powers and even factorials but alternating signs. You probably don't recognize it right away because we've only barely been introduced to it. And here it is, the cosine. See those even powers on x with the same factorial on the bottom, alternating signs, but there's a 1 here in the front, and ours has a 5. So there's a couple things we're going to have to tweak over here. Let's get a 1 there. Let's just pull apart that 5. 4 plus 1 plus, and then the rest of this. From here on, that's just the series for cosine of x, but specifically when x is 2. Oh, wait, I just recognized a mistake. We have an issue here. The signs are not alternating in the correct way because it starts positive 1 and goes positive, and then it starts alternating. We actually want a negative 1 here to start because the series for cosine starts at positive 1 and then goes to negative 2 squared, but we are forced to switch the sign of that because these signs are offset. This is actually want to change this to 6 minus 1, break apart 5 that way, so that negative 1 plus 2 squared over 2, that's a series expansion for negative cosine of 2, which means that this series should become 6 minus cosine 2. From this point on is all negative cosine 2, and you can think of it as saying 6 plus all that. Okay, notice how we're getting closer and closer to the actual answer of 6 minus cosine 2. Then minus 2 to the 8 over 8 factorial. Even closer. Let's just do one more. Plus 2 to the 10th over 10 factorial. We can see that we have a series that is converging to 6 minus cosine 2. All right, and there is the end. This often is the chapter that is considered the most difficult in Calculus 2, but the more you wrestle with it, the more interesting the ideas become, and they are actually very useful in upper mathematics.